Hope you are able to see my screen. All able to see my screen? Okay, fine. So let's start. So in the last class, what we were doing was we were defining what do you mean by a finite automata. And not only finite automata, we describe what do you mean by a deterministic finite automata. So we gave a formal definition and then said that it is a quintuple Q sigma delta Q naught comma F. So if I want to represent the finite automata, if you are asked to give a finite automata, you need to give all these 5 quintuples. Okay, so what is a set of state? What is a set of input alphabet? What is the transition function that you are using? What is a Q? Which is the start state, that is Q naught, and which is the set of final states, which is a subset of Q. So all these things you need to give. Then only you will be able to define this finite state automata. Okay. So now let us say, suppose you have a finite automata like this. So let me call this as a FA. FA is a finite automata. Okay. So when will I say that finite automata accepts a string? Okay. So let us take a string W. So W is a string that can be represented as A1, A2, etc., AN. So there are n symbols in that string. Okay. So you can consider string as a word also. So if you want to more have an intuitive kind of understanding, you can always consider the string as a word. So word is nothing but it consists of symbols, right? And here the symbols are A1, A2, AN, and there are n symbols now. Okay, so that's what we are representing it as A1, A2, AN, right? So now, when will we say that the FA accepts the string W, right? So that's what we are trying to explain. And FA accepts a string W, where W is nothing but A1, A2, etc., AN, if there is a path in the transition diagram that has these 3 things. One is begins at the start state, ends at an accepting state or final state. Any final state is also called as accepting state. Okay. And the third point is has a sequence. The path should have a sequence of labels A1, A2, etc., AN. Okay. So this is what is the definition of when we will say that finite state automata accepts the string. Okay. So let's see one example, then it will become a little more clear. So we will take up the finite automata that we had seen in the last class. Okay. So let me draw that again for you. So this is a Q naught, and there is a transition which is labeled as 1, right? If it is 1, it will be in Q naught itself. And then on reading a 0, it goes to the state Q2. And on reading a 0 from Q2, it will remain in Q2 itself. and then on reading a 1, it will be in the final state, that is Q1. Okay, and from Q1 it can read whatever the symbol, it may be 0 or 1, it will be remaining in the Q1 state itself. Okay, so this is one automata. Now can we say that one string? So let us take one string, very simple string first of all. So 1 0 1 1. Let us take this string and then see that whether this is accepting or not. So let us start with the Q0, right? So let's start with the Q0. So it is in Q0 now. So with the Q0, it is reading a 1. Okay, so it is starting with Q0, and after reading a 1, it will remain in Q0 itself, right? So it has a self loop, right? And then once it reaches 0, it will go to Q2, right? So once it reaches 0, it reaches Q2. So after reading a 0, it is now in Q2. Now in Q2, it is reading a 1 again, right? So then it will go to Q1. It will go to Q1. Now from Q1, it is reading a 1 and it will remain in Q1. So it will remain in Q1. So now you have a path. It is starting with Q0, it is reading a 1, it is going to Q0 according to the transition diagram. And then from Q0, it is reading a 0, it is going to Q2, and Q2, it is reading a 1 and it is going to Q1. And from Q1, it is seeing a 1 and it is remaining in Q1. Right? So you start with the Q0, this is the start state, and you end up with the Q1 after reading all the symbols, and now Q1 is a final state. So you are reaching a final state of after reading all the symbols. Then that means this string will be belonging will be set as accepted. So this string is accepted by the given finite automata. Okay, so now let us take another string which is not accepted by this automata. So let's take 1 1 0 0. This will not be accepted because there is no 0 1 here. Okay, so now let's see what is happening in the finite automata. So it starts with 1, so it is starting with Q0. Okay, so this is Q0. It is reading a 1. And it is remaining in Q0 itself. Okay. Now, it is again a 1. So there is second one. And after reading the second one also, it will remain in Q0 only. Because there is a 1, that is the only transition there for Q0 and 1. Right. And now, it is seeing a 0, which is the third symbol. So after it sees a 0, it moves from Q0 to Q2. So it will be remaining in Q2 now, after reading the first 0. But from Q2, if it sees a 0, it will remain in Q2 itself. So it will remain in Q2 itself. Now, you see that it has read all the symbols 1 1 0 0, but and starting with the Q0, but it is ending with the Q2, which is not a final state. So if you read all the symbols which is there in the string, and then you remain after reading all the symbols, you are in a non-final state or a state which is not a final state, then it will not be accepted, not accepted by a SA. So this string is not accepted, but this string is accepted. Okay. So now there are two concepts. One is some string which are accepted and some string which are not accepted, right? So now if I so here the alphabet is 0 comma 1, right? So the alphabet is 0 comma 1. So now if I consider sigma star, what is sigma star? Sigma star is nothing but 0 comma 1 star. So 0 comma 1 star is nothing but any word over zeros and ones. Now I can, so whatever the string that I take from sigma star, that is W from sigma star, there are only two cases. One case, the W is accepted by FA. The second case is W is not accepted by FA. So these are the only two cases you will have, right? You take any string from the alphabet over the alphabet sigma. There are only two cases. One, it is accepted by FA, and the other one which is not accepted by some FA, right? So now I will collect all the strings which are accepted by the FA. Whatever the string that is accepted by the FA, W accepted by FA, I will take as a set, whatever be the string W belonging to sigma star. And that is called as the language accepted by the finite automata FA. So you collect all the strings which are accepted by the finite automata by the previous method that we had seen, right? And you call that set of strings accepted by the finite automata as the language accepted by the finite automata. Understood the definition? Is there any doubt? Let me go back to the chat window. Any clarifications you require? Any questions? Okay, fine. So let's continue. So W accepted by FA, where W belonging to sigma star is collected as a set, and we call that as a language accepted by the finite automata. Okay, so this is a little bit informal definition. Okay, now let's make it a little more formal. So we had talked about what do you mean by a transition function when we define the finite automata. So delta is nothing but a function from Q cross sigma going to Q, where Q cross sigma is your domain and Q is your codomain, right? In terms of the function. So you will have something like this, right? So delta of Q comma A is equal to some P. What does that mean? Is you are in the state Q, you are reading a symbol A, and then you are going to a state called P. That's what it means. That's what it means, right? So now I'm trying to extend this definition of delta, which is for only one symbol, to delta cap. So delta cap is a function from Q cross sigma star going to Q. It is an extension of the function. Okay, so let's see how we are defining that. So these are two things you need to take care. One is the basis and the other one is the induction step. The basis is, so delta cap of, so I need to now explain. So Q cross sigma star means what? So sigma star means it can have epsilon also, and it can have any word over sigma also, right? So now I need to explain what do you mean by what is the function of this, what is the mapping of this delta cap for string like empty string epsilon. Okay, so delta cap of Q comma epsilon is given as Q, and the induction step is, so this is an inductive definition. Okay, so it is also called as a recursive definition. Okay, so delta cap of any string, delta cap of Q comma XA means XA is a string where X is a suffix, X is a prefix and A is one symbol. Okay, so for example, if I'm taking the string A1, A2, AN, I'm taking XAN. That's what it means. So the first n minus 1 symbol, that is a prefix, I'm taking it as X, and an is the last symbol in that string. So that's what I'm taking. So the previous class I had mentioned about the notion, right? X means it is a string and A is a symbol, right? So that's what the notion that we are following here. So X is a prefix, also called, we can also say it is a substring, but it is also a prefix. And A is a symbol which is concatenating with that, right? So delta cap of Q comma XA is given as here delta cap of Q comma X comma A. That is the definition of delta cap. So you are explaining what is delta cap in terms of delta and delta cap, where within that delta cap you have a string which is of lesser length. So XA is of length n. Here the X is of length n minus 1. Okay, so that's how you are recursively defining that that function which is called as a delta cap. Okay, so delta cap is the extension of the definition of delta. That's all. So delta is for only one symbol at a time. That's what we defined in the case when we defined the finite automata. But if you are extending the delta to delta cap becomes a function over the strings rather than one symbol, right? It will be a function over the strings, right? So have you all understood this? Any clarifications until this point? Any questions? Okay, fine, right. So let me continue then. Now we can define formally what do you mean by the language accepted by the finite automata FA. So language accepted by the finite automata is given as the set of all string belonging to sigma star such that delta cap of Q naught comma W belongs to the capital F. So how will you read this? The language of F of A is FA is nothing but the set of all string W belonging to the alphabet set of all string over the alphabet set sigma, such that if you apply the delta cap function from Q naught comma the string W, you will end up with the final state. That's what it means. After reading all the symbols in W, you will end up in a final state. That's what it means. Okay, so that's a formal definition of a language accepted by the finite state automata. Okay, so sometimes I call it as finite state automata, sometimes I call it as finite automata. Both are the same. Okay, don't get confused with that. Now, you take any language accepted by the finite automata, that language is called as a regular language. Any automata that accepts a language, that language is called as a regular language. Fine. Now let's see some examples. Let us take the same example that we had seen. Okay. Now I want to explain you some something that I was noting it down in the previous class. Like in the previous class also we saw the same example actually, right? But we did not say why we are remaining in Q naught itself if we are reading a 1, Why we are shifting to Q2 if we are reading a 0, and from Q2 if you are reading a 0, you are remaining in Q2 itself, and you are moving to Q1, you are transiting to Q1 on seeing a 1 from Q2, right? And from Q1, you are remaining in the same state, whatever be the string that you are, whatever the symbols that you are reading, right? So what is the idea behind it? Now you see, what is the language accepted by this finite automata? The language accepted by this finite automata is, we had seen in the previous class, is x01 y, where x comma y belongs to 0 comma 1 star. So x and y can be any string over 0 comma 1. Okay, right. So let's see how this works out. Now, what is the pattern of this string actually? The pattern of the string is, you are having x, you are having y, and both are like, x is a suffix and y is a x is a prefix and y is a suffix, and x and y are any string over the alphabet 0, 1. So you don't bother about whatever the symbol that it is going to read. So you don't have to bother about it. What you should bother about is the substring 0, 1. Because you need to make sure that the string contains 0, 1. So whenever you read a 0, that might be the starting point of the 0, 1. Right? So you need to store that information that you have read a 0 and you have read a 1. Somehow the machine has to store that information that it has read 0, 1 or not, right? And for that, what are we doing here? So let's see. Let's now go back to the same automata that we had seen. So now, whenever you are in Q0, if you are reading a 1, it doesn't matter because it is not the starting point of 0, 1, right? So you don't have to consider about whenever you are reading a 1. So you can be in the same state. But whenever you are starting to read a 0, what you do? You go to Q2. And then Q2 is a state which remembers the fact that you have read at least 1 0. You have read at least 1 0. Because from Q2 itself, you can read some zeros. Any number of zeros you can read from Q2 itself. Right? So, but Q2 always stores an information that it has read at least 1 0. So that is the beauty of this Q2 state. Q2 remembers that fact, right? So it is making sure that it has read at least 1 0. Now, if it sees a 1, then immediately it goes to Q1. And from Q1, you are making sure that you have already made sure that you have read at least 1 0 followed by a 1 1. So from Q1, you can read whatever the string that you want because you have already made sure that it is having 0 1, right? Without 0 1, you will not be able to reach Q1 at all. And Q1 is a final state. So after reaching the final state, you can read whatever string that you want to have, right? So 0 1 is one substring that you need to have in whatever the string that is accepted by this automata, finite automata. And to store that information, we are having a state Q2 and we are having a state Q1, so in which Q2 makes sure that it stores that information that you have read at least 1 0, and Q1 stores the information that you have read 1 followed 1 with a previous symbol as 1 0, right? And so after reaching Q1, you already have guaranteed that you have read the 0 1 as a substring in the whatever the string that it is going to be read by the automata. So from Q1, you can read whatever symbol that you want. So from 0 or 1, whatever symbol you read, you will remain in Q1 itself. And that is what we are doing here. So now you see here, for this example, 1 I read, so it is remaining in Q0 itself because it is not part of the 0, 1, right? So whenever it reads a 0, it goes to Q2. So now it means that it has read at least 1 0, right? And from 0, it is again reading of 1. So it is going to Q1. So from Q1, you are dead sure that you have read 0, 1. So from Q1, you can read whatever the string that you want. So likewise, I can also accept 1 0 1 0 0 0 0 0 like that, or 1 also followed by 1, whatever be the thing. Because from after reading 0 1, you will go to Q1 always. And from Q1, you can read whatever the string that you want to have. And that is the beauty of this finite automata. So did you understand the concept why we are having these number of states? This finite state cannot be, this finite automata cannot be minimized with a less number of states, because you need to remember the 0 and you need to remember the 1 also, right? So Q2 remembers the fact of seeing a 0, and Q1 remembers the fact of seeing 0, 1. So you need to have at least 2 states other than Q0. So you need to have at least 3 states to do this automata. Okay, so this is an example of a finite automata that accepts a string W in such a way that W has a 0, 1 substring in it. So any doubt on this? Let me pause for a few minutes and let me wait for your queries if you have anything. Could you show for X101Y? Yeah, it's, see, whenever you are seeing 1 0, you are already in Q1, right? So let me go back. So X101Y, right? X101Y. X101Y. So whenever you are reading 1 0, you will be in Q1 always. So here itself you will be in Q1. And from Q1, you can read whatever the string that you want to have. From Q1, you cannot go to any other state, right? Once you reach Q1, Q1 is a black hole for you. You cannot come out of the black hole. Some people call it as a dead state. Dead state means you will be in the same state actually. You will not be able to go out of that state at all, right? So whatever the things remaining, you can read there. So Y can be any string, right? That answers your question? One zero one zero 1 0, right? So that's what we see. Whenever it reads a 1 0, it will go to Q1. So from Q1, it can read whatever it wants. Then after the first 0 1, then other 0 1 will be in Q1. No, once it reaches Q1, it cannot go out of it, right? So it will remain in Q1 itself. So with 101, right? So you are starting with 101. So 101, after reading the third symbol, it will go to Q1. And from Q1, it can read whatever it wants. Yeah. You can check it. You can check it. So just, it will reach at end. What do you mean by that? See, you have here 1 0 0, 1 0 is there. So see, 1 0 0 0 1 is there, right? See, what is that string? 1 0 0 1 0 0 1, right? So let me go back to that. 1 0 0 1 0 0 1, right? See, this is 0 1 is there, right? 0 0 1, I mean. So 0 0 1 means what? 0 0 1. So it will reach Q1. So after reading 0 1, here it will be in Q1, and from Q1 it can read whatever it wants. So that also will be accepted. Whenever there is a substring 0 1, it will be accepted. That is this automata. That's the beauty of it. I didn't get your question. What is this? So whenever there is a 0 1, it will accept. That's all. Whether it is x1 0 1 y or whatever, it is having 0 1, right? If it is having 0 1, it will reach Q1, and from Q1 it can read any y. That you can try. I will give one example. So if it is having 1 0 1, you need to have another state. You need to have another state which will remember the fact that it has to read another 1 also, followed by 1 0. So you need to have another state. That's all. So you can draw it. You have got the concept, means you will be able to get for any kind of string like this. Actually, you can go for, like, for example, so here I am talking about x01y. You can also talk about x101y. You can talk about x0001y. So how many symbols that you need to have? That many states you want plus 1. Okay, so 0 1 means you need to have 3 states. Okay, so 1 0 1 means it is 3 plus 1, so 4 states you need to have. 0 0 0 1 means you need to have 4 plus 1, 5 states. I have given some hint. You can draw the automata. Okay, so that will be your exercise. Now let me take another example for you, which is also a very interesting example. So example 2. So this is a quite interesting example. So Q0 is your start state, and there is another state called Q1, and there is another state called Q2, and there is another state called Q3. And Q0, on reading a 1, it goes to Q1, and from Q1, on reading a 1, it goes back to Q0. Q1, if it reads a 0, it goes to Q3, and Q3, on reading a 0, it goes back to Q1, and Q3, if it reads a 1, it goes to Q2, and Q2, if it reads a 1, it goes to Q3, and Q0, if it reads a 0, it goes to Q2, and Q2, if it reads a 0, it goes to Q0. Okay, so this is your automata now. Okay, so now let me make this thing very clear. Whenever you are drawing an automata, right, so you need to label the states, you need to label the arcs also with the directions. Okay, you need to label every edge that is a directed edge with the input alphabet. What input alphabet you are using to transit from one state to another state. Okay, so that is very important. If you miss it out, then it will be a problem. Okay. So, and you also need to mention about which state is a start state by using this arrow, and which state is a final state just by putting two concentric circles. Okay, so this is your automata now. Now, let me ask you this question. What? So, can you tell some few strings that will be accepted by this automata? So, can you list out some of the strings that is accepted by this automata? Yeah, can you tell me? You can open your mic and then tell. Just tell some strings which are accepted. You know what do you mean by accepted, right? Yes.
Sir, 1010.
1010. How it is accepted? So 1 0 1 0. Yes, 1010 is accepted. Any other string? What about 1 1? 1 1, yes. Likewise 0 0. And 1 0 0 1. 1. So 1 0 0 1. Right? So 1 0 0 1 is also accepted. And then 1 1 0 0. 1 1 0 0. So 1 1 0 0 is also accepted. And then any other strings you have? 1 1 1 1 0 0 0 0. All these things are accepted. You can check. Any other strings? Can you tell me? Any other strings? 0 0 1 1.
0
Yeah.
0 1.
Huh? 0 1
0 1.
0 1. How 0 1 will be accepted?
0 1 0 1.
0 1 0 1. Okay, fine. 0 1 0 1. Yeah, 0 0 0 1 0 1 is also accepted. Yes. Now, do you find any kind of a pattern that is emerging? Epsilon also will be accepted, right? Because Q naught is a start state and it's also a final state, right? So empty string is also accepted there. So any other strings? Or can you generalize this? What kind of strings that you are getting here? Yes, quickly. It's not very difficult. Just try to guess it. You will be able to tell me. The last batch, they found out the answer. What is the pattern that you are having here? In all these things.
Sir, the number of zeros and ones are equal.
We can't say that. It's not equal actually. So see, we can also accept 0 0 1 1 1 1. See that?
Yes, sir. Okay.
So it's not equal number of ones and zeros. So it is something else. What is that?
So even number of
Even number of
zeros and ones.
even number of zeros and even number of ones. That is what it will be accepting. Okay. So the language will accept even number of zeros and even number of ones. A simple automata with 4 states, symmetrical in nature, is able to accept an infinite number of strings, which is having a specific pattern in which the number of zeros is even and the number of ones is even. See how beautiful it is. With a finite representation, you are able to give a specific pattern that is emerging when it is accepting a string, right? So how it is doing this? So can you try to explain it? Can you guess what we are doing here? Can you guess? So I'm not trying to find out the correct answer from you, but you can think and then tell me what is making this automata to accept even number of ones and even number of zeros.
Sir,
Yes?
the information stored by the state.
What is the information that is stored in the state? Can you tell me?
The strings we are giving as input.
No, the strings are given as input to the automata, fine. But what is the significance of this Q0? What is the significance of the state Q1? What is the significance of the state Q3? And what is the significance of the state Q2? That's what I'm trying to ask. Then once I tell that, you will be able to easily say that how this is going to happen. So can you give me the significance of Q0, Q1, Q2, and Q3? Why is it defined like this? What is Q0 storing? Some information. And what is Q1 storing an information? What kind of information the Q3 is storing? And what kind of information Q2 is storing here? So what you need to store here, whether you have read odd number of zeros or even number of ones. Right? Odd number of zeros or odd number of even number of zeros, or odd number of ones or even number of ones, right? So you have four possibilities. It can be odd, or it can be even. It can be odd, even, or it can be even, odd. These are the only four possibilities, right? So when you start with, you have read only zero number of zeros and zero number of ones, and that is even. So Q0 is corresponding to even. And once you read 10, you are going to Q2. And Q2 stores information like it has read odd number of zeros but even number of ones. So Q2 is odd, even. It is storing that information. And this is even. So let me put E, okay? And this is O, E. And this is what? So here you are having odd, even, and you are reading a 1 and then going to Q3. So this is going to be odd. And this is going to be what? The other case. You are already in even and you are reading a 1, and so the number of ones becomes odd, right? So it will be even, odd. Now you tell me. Now you can find out whenever you want to reach even, right? So whenever you reach Q0, it means that you have read even number of zeros and even number of ones, because Q0 is a final state. So whatever be the string, you will reach Q0 only when you have read even number of ones and even number of zeros. And that is what is this beauty of this automata. Okay. So when Q0 is Q0 is a final state, it will accept even number of ones and even number of zeros. But now, can I ask you another question? So if I want to find an automata for accepting all the strings with odd number of zeros and odd number of ones, can you tell me what will be the change we need to make here?
Q3 will be the final state.
Q3 will be the final state, and make a Q not non-final state. That's all. Simple. And similarly, if I make Q1 as a final state and all other non-final states, then it will accept even number of zeros and odd number of ones. And if I make Q2 as a final state and all other states as non-final state, then it will accept odd number of zeros and even number of ones. That is the beauty of this automata. A symmetrical automata that gives a very good, very simple kind of a pattern, which is kind of infinite description, but with infinite language, I mean infinite set with only finite description. Okay, that is the beauty of this automata. If we have understood this concept, then we can go ahead with more and more examples, and that will give you more and more depth into the finite state automata, how to define a finite state automata for a specific language. Okay, so both the ways will be you have to train yourself. Given a language, how to draw a finite state automata which accepts that language, or given an automata, what is the language it is accepted by this finite automata. Both the ways we need to make sure that we are comfortable. Okay, so for that you need to do more and more exercises from the Hopcroft-Ullman and Peter Linz and such kind of books. Okay, so there are many worked out examples also. Maybe you can first go through the worked out examples and then get more and more clarity, and then you can attempt some very basic exercise problems. Okay, so I will also be posting some exercise problems, not only exercise problems, some simple problems also for you to understand how this automata works, so that once you get hold of this finite state automata, you will be able to get hold of the push down automata, the Turing machine, such kind of things. Because the basic thing here is the finite state automata. If you have understood this concept well, you can understand any of the other concepts very easy, because this is the most simplest mission. If you have understood this, you will be able to understand all the other things also. But if you have not understood this, then please ask me questions, and then you need to have more clarity and read the book also, the Hopcroft-Ullman and Peter Linz. So especially you try to read those books and then try to get more and more depth into this. If you are not able to, please ask me. I will try to clarify as much as possible, so that you will get more familiar with this finite automata. Okay, so let me stop the class for today. I will give you a few more minutes. If you have any doubt, you can ask me. Can you give an example of a non-regular language? We will come to that. Okay, so the palindrome is a non-regular language. Any palindrome. Or you can, we had also talked about 0 power n, 1 power n, equal number of zeros followed by equal number of ones. That is also a non-regular language. But how to prove that non-regular language, it's a difficult task. That will be shown by using one theorem called as a pumping lemma. And that pumping lemma will be useful for you to prove some of the language is not regular. What is Q called? Q is a set of states.
Sir,
Yeah.
sir, can you please explain question 2 once again? How we get even, odd even?
Yeah. See, when you are starting the processing, you are seeing Q naught, right? And that means you have not read any symbol. So you have read 0 zeros and 0 ones. That is even, right? So 0 number of ones and 0 number of zeros is even. That is what it is, even, EE. And once you read a 1, the number of 1 becomes odd. A number of 0 is still even. So that is why we are going to even odd. Likewise, if I read a 0, it means that it has read an odd number of ones and it is still even number of zeros. So that is why we are going to odd even. And likewise, from Q2, if I'm reading a 1, then the number of 1 also becomes odd. So you are going to odd odd. And likewise, if you are in Q1 and you are reading a 0, then the number of 0 which is even will become odd, right? So it will become odd odd. And like that's what we are doing right now here. Fine?
Okay, sir. Got it. Thank you.
Yeah, yeah. Okay then, so if you don't have any questions, let's stop this class for today. We will meet again on Wednesday. Bye all of you.